Because of the connection between definite integrals and antiderivatives, it's really nice to have some notation to refer to the antiderivative of a function. And this is the notation we'll use. So this notation indicates the antiderivative of the function little f. Remember that this is a function of, this whole expression denotes a function of x. So unlike a definite integral, this antiderivative notation, which is also called an indefinite integral, this notation refers to a function of x, and in fact a whole family of functions of x, because little f has many antiderivatives and all of them differ by a constant. So this is actually a whole collection of functions and not just a single function. So we'll call this the antiderivative of f, or the indefinite integral of f. This notation is especially nice because a definite integral looks like this, where you have bounds, and an indefinite integral, right, looks like this, without bounds. But if you have an indefinite integral, that's an antiderivative, and if you evaluate at a and b and subtract, you actually get the same thing as the definite integral. This is essentially the content of the second part of the fundamental theorem of calculus, right? So our notation is really helping us here because these two things look the same, and indeed they are the same. That's a sign of good notation when things that look true are true. So because of the connection between definite integrals and antiderivatives, we actually know a lot of, I guess you could call them rules for antiderivatives or integrals already. In fact, every derivative rule gives you an antiderivative rule as well, which is essentially an integral rule. If you look at any textbook, any calculus textbook, so here I'll look at the OpenStack's calculus textbook, it will have some sort of table of antiderivatives, but since an antiderivative is an indefinite integral, this is really a table of integrals as well. So if we look at this table, there it is, right? Every differentiation formula has a corresponding indefinite integral formula, and there are lots and lots of them, right? So the derivative of a constant is 0, and the power rule here, derivative of x to the n is n times x to the n minus 1. If you just work this backwards, you get an integral rule, which says, right, instead of the power going down by 1 and you multiply by the old power, the power goes up by 1 when you integrate, and you divide by the new power. For all of these indefinite integral rules, notice they all have a plus c, and that's because the indefinite integral refers not just to a single function of x that's an antiderivative, but the whole family of antiderivatives, and all of the antiderivatives differ by a constant. So that's what the plus c is doing here. Whenever you calculate an antiderivative, it's important to write that plus c, that unknown constant, because you don't initially know what it ought to be for whatever application you're working on. So it's important to never forget that constant of integration, as it's called, the plus c. All right, so with that in mind, let's look at some examples of calculating some integrals. Now, one thing that's important to realize as you're working with integrals is that you shouldn't make guesses about antiderivatives without checking your guess. So let's work on this example, the integral. This is a definite integral from 4 to 9 of the square root of x times x plus 1 dx. So one thing that people often do with this sort of thing is they'll see this product here and they'll say, okay, so this is the integral from 4 to 9 of the square root of x dx times the integral from 4 to 9 of x plus 1 dx. But is there actually, what they did here is they broke up the integral at the product, but is there any differentiation rule that lets you just split up a derivative at a product? No, there isn't. That's not the product rule for derivatives, and so this isn't the product rule for integrals either. So you do have to be a little careful to not accidentally make up false integral rules. So we can't split this up at the product. So we need to come up with some other way of handling this integrand. Just randomly guessing antiderivatives probably isn't going to be too productive. But remember, you can always do algebra on your integrand before you actually integrate. So for example, we could distribute this square root. When we do that, so we're just doing algebra, we aren't doing the antiderivative yet, so the integral symbol still is hanging around. And then for the algebra on the integrand, square root of x times x is x to the 3/2. And then square root of x times 1 is square root of x. Okay, now this looks like something we could guess an antiderivative for, or use the power rule for antiderivatives if you want to look at it that way. The antiderivative for x to a power, right, the power goes up by 1, so that's going to give us x to the 5/2, and then you divide by the new power, so that's going to put a 2/5 out here. Now, as soon as you write something like this down, it is a good idea to check that this is the correct antiderivative just by mentally taking the derivative of it quickly and checking that you get back where you came from. And indeed, if you take the derivative of 2/5 x to the 5/2, you do get x to the 3/2. So this is the right antiderivative, and now we'll continue on writing down our antiderivative. So the square root of x, this is really x to the 1/2. So we can again use the power rule. We're going to add 1 to the power, so we get x to the 3/2, and then divide by the new power, so 2/3 out here. All right. Now, if this were an indefinite integral, we would need to write plus c here for our constant of integration, but this is a definite integral, so we just need to evaluate. So this is 2/5 times 9 to the 5/2 plus 2/3 times 9 to the 3/2. So that's plugging in the top bound, and then minus, and then we'll plug in the bottom bound. 2/5 4 to the 5/2 plus 2/3 4 to the 3/2. And at this point, this is just a bunch of arithmetic that we can do. So let's see, we'll do maybe one more step until we, I don't know, get tired of working with the fractions, I guess. So 9 to the 5/2, so the square root of 9 is 3, and 3 to the 5th power is, oh boy, 3 to the 5th power is 9 times 3, so 81 times 3, so it's going to be 243, so times 243 plus 2/3 times 9 to the 3/2, so again, square root of 9 is 3, 3 cubed is 27, minus 2/5 times, so let's see, square root of 4 is 2, 2 to the 5th is, let's see, 1st, 2nd, 3rd, 4th, 5th, so 32. 32 plus 2/3 times 2 to the 3rd, that's 8. Okay, I'm already tired of working on the arithmetic, so at this point it's all arithmetic, right? Okay, so let's look at another example. How about this indefinite integral? Notice this is an indefinite integral. There aren't any bounds here. So what we're expecting as a final result is a family of functions of x, not a number. So let's see. But, you know, we have a quotient here as our integrand, and there's no easy quotient antiderivative rules, so we need to do something else to make it so that we can guess an antiderivative. And, you know, what that something else is really depends on what the integrand is. And for this particular integrand, it looks like we could simplify this just by doing this division. So we'll do the integral in a moment, but just working on algebra and the integrand, this is 3x minus 4 plus 1 over x. Okay. And now we can write down an antiderivative for each piece, right? This is a sum of 3 terms, and so the sum rule for integrals says we just integrate each piece. So the integral of the first piece, antiderivative of this first piece, is 3/2 x squared minus, and now integral of the second piece is 4x plus integral of 1 over x. So we're looking for a function whose derivative is 1 over x, and that's natural log. So natural log x. And then remember, this is an indefinite integral, so we get a function of x as a result, but don't forget to add your constant of integration, right? You must write down your constant of integration when you're doing an indefinite integral. So I think the lesson to take from these two examples is, don't forget that you can do algebra on your integrand to turn it into something that's easier to guess an integral for, or guess an antiderivative for, and don't forget your constant of integration.